In this video, we're going to begin our discussion of parsing technology with context-free grammars. Now, as we know, not all strings of tokens are actually valid programs, and the parser has to tell the difference. It has to know which strings of tokens are valid and which ones are invalid and give error messages for the invalid ones. So we need some way of describing the valid strings of tokens and then some kind of algorithm for distinguishing the valid and invalid strings of tokens from each other. Now, we've also discussed that programming languages have a natural recursive structure. So, for example, in COOL, an expression can be any one of a very large number of things. So two of the things it can be are an if expression and a while expression. But these expressions are themselves recursively composed of other expressions. So, for example, the predicate of an if is itself an expression, as is the then branch and the else branch. And in a while loop, the termination test is an expression, and so is the loop body. And context-free grammars are a natural notation for describing such recursive structures. So what is a context-free grammar? So formally, it consists of a set of terminals, T, a set of non-terminals, N, a start symbol S, and S is one of the non-terminals, and a set of productions. And what's a production? A production is a symbol followed by an arrow followed by a list of symbols. And these symbols, there are certain rules about them. So the X thing on the left-hand side of the arrow has to be a non-terminal. That's what it means to be on the left-hand side. So the set of things on the left-hand sides of productions are exactly the non-terminals. And then the right-hand side, every YI on the right-hand side, can be either a non-terminal, or it can be a terminal, or it can be the special symbol epsilon. So let's do a simple example of a context-free grammar. Strings of balanced parentheses, which we discussed in an earlier video, can be expressed as follows. So we have our start symbol, and one possibility for a string of balanced parentheses is that it consists of an open paren, another string of balanced parentheses, and a closed paren. And the other possibility for a string of balanced parentheses is that it's empty, because the empty string is also a string of balanced parentheses. So there are two productions for this grammar, and just to go over the to relate this example to the formal definition we gave on the previous slide, what is our set of non-terminals? It's just the single non-terminal S. What are our terminal symbols in this context-free grammar? It's just open and closed paren. There are no other symbols. What's the start symbol? Well, it's S. It's the only non-terminal, so it has to be the start symbol. But generally, we will, when we give grammars, the first production will name the start symbol. So rather than name it explicitly, whichever production occurs first, the symbol on the left-hand side will be the non-terminal for that particular context-free grammar. And then finally, what are the productions? Well, we said it could be a set of productions, and here are the two productions for this particular context-free grammar. Now, productions can be read as rules. So let's write down one of our productions from the example grammar. And what does this mean? This means wherever we see an S, we can replace it by the string of symbols on the right-hand side. So wherever I see an S, I can substitute in. I can take the S out. That's important. I remove the S that appears on the left side, and I replace it by the string of symbols on the right-hand side. So productions can be read as replacement rules. The right-hand side replaces the left-hand side. So here's a little more formal description of that process. We begin with a string that has only the start symbol S. So we always start with just the start symbol. And now we look at our string. Initially it's just a start symbol, but it changes over time. And we can replace any non-terminal in the string by the right-hand side of some production for that non-terminal. So for example, I can replace the non-terminal X by the right-hand side of some production for X. In this case, X goes to Y1 through Yn. And then we just repeat step 2 over and over again until there are no non-terminals left, until the string consists of only terminals. And at that point, we're done. So to write this out slightly more formally, a single step here consists of a state, which is a string of symbols, and these can be terminals and non-terminals. And somewhere in this string is a non-terminal x, and there is a production for x in our grammar. So this is part of the grammar. Okay, this is a production. And we can use that production to take a step to a new state where we have replaced x by the right-hand side of the production. Okay, so this is one step of a context-free derivation. So now if we want to do multiple steps, we could have a bunch of steps. Alpha 0 goes to alpha 1, goes to alpha 2, and these are strings now. These alpha i's are all strings. And as we go along, we eventually get to some string alpha n, all right? And then we say that alpha 0 rewrites in 0 or more steps to alpha n. So this means in 0 greater than or equal to 0 steps. Right? So this is just a shorthand for saying there is some sequence of individual productions, individual rules being applied to a string that gets us from the string alpha 0 to the string alpha n. And remember that in general we start with just the start symbol, and so we have a whole bunch of sequence of steps like this that get us from the start symbol to some other string. So finally, we can define the language of a context-free grammar. So let G be a context-free grammar. It has a start symbol S. So then the language of the context-free grammar is going to be the string of symbols, alpha 1 through alpha n, such that for all I, alpha I is an element of the terminals of G. Okay, so T here is the set of terminals of G. And S goes, the start symbol S goes in 0 or more steps to A1 to AN. Okay? And so what is this saying? This is just saying that all the strings of terminals that I can derive beginning with just a start symbol, those are the strings in the language. So the name terminal comes from the fact that once terminals are included in the string, there's no rule for replacing them. That is, once a terminal is generated, it's a permanent feature of the string. And in applications to programming languages and context-free grammars, the terminals ought to be the tokens of the language that we are modeling with our context-free grammar. With that in mind, let's write a context-free grammar for a fragment of cool. So cool expressions, we talked about these earlier, but one possibility for a cool expression is that it's an if statement or an if expression. And recall that cool if statements have 3 parts, and they end with the keyword phi, which is a little bit unusual. And so looking at this particular rule, we can see some conventions that are pretty standard and that we'll use. So the non-terminals are in all caps. All right, so in this case, it's just one non-terminal, but we always write it out in caps. And then the terminal symbols are in lowercase. All right. And another possibility is that it could be a while expression. And finally, a last possibility is that it could be an identifier ID. And there are actually many, many more possibilities. There are lots of other cases for expressions. And let me just show you one bit of notation to make things look a little bit nicer. So when we have many productions for the same non-terminal, we usually group those together in the grammar. And we only write the non-terminal on the right-hand side once. And then we write explicit alternatives. So this is actually completely the same as writing out x per arrow 2 more times. But this is just a way of grouping these 3 productions together and saying that EXPR is the non-terminal for all 3 right-hand sides. Let's take a look at some of the strings in the language of this context-free grammar. So a valid cool expression is just a single identifier, and that's easy to see because EXPR is our start symbol. I'll call it expr. And there's a production that just says it goes to ID. So I can take the start symbol directly to a string of terminals. A single variable name is a valid cool expression. Another example is an if expression where each of the sub-expressions is just a variable name. So this is perfectly fine structure for a cool expression. Similarly, I can do the same thing with a while expression. I can take the structure of a while and then replace each of the sub-expressions just with a single variable name, and that would be a syntactically valid cool while loop. There are more complicated expressions. So for example, here we have a while loop as the predicate of an if expression, not something that you might normally think of writing, but perfectly well formed syntactically. Similarly, I could have an if statement or an if expression as the predicate of an inside of an if expression. So nested if expressions like this one are also syntactically valid. Let's do another grammar, this time for simple arithmetic expressions. So we'll have our start symbol and only non-terminal for this grammar be called E. And what are the possibilities? Well, E could be the sum of expressions. Or, and remember this is an alternative notation for E arrows. It's just a way of saying I'm going to use the same non-terminal for another production. We could have the sum of two expressions, or we could have the multiplication of two expressions. And then we could have expressions that appear inside of parentheses, so parenthesized expressions. And just to keep things simple, we could just have as our only base case simple identifiers, so variable names. And here's a small grammar over plus and times. It's in parentheses and variable names. So let's look at a few elements of this language. So for example, a single variable name is a perfectly good element of the language. ID plus ID is also in this language, as is ID plus ID times ID. We could also use parens to group things. So we could say ID plus ID close paren times ID. That's also something that you can generate using these rules, and so on and so forth. There are many, many more strings in this language. Context-free grammars are a big step towards being able to say what we want in a parser, but we still need some other things. First of all, a context-free grammar, at least as we've defined it so far, just gives us a yes or no answer. Yes, a string is in the language of the context-free grammar, or no, it is not. We also need a method for building a parse tree of the input. So in those cases where it is in the language, we need to know how it's in the language. We need the actual parse tree, not just yes or no. In the cases where the string is not in the language, we have to be able to handle errors gracefully and give some kind of feedback to the programmer, so we need a method for doing that. And finally, if we have these two things, we need an actual implementation of them in order to actually implement context-free grammars. One last comment before we wrap up this video. The form of a context-free grammar can be important. Tools are often sensitive to the particular way you write the grammar. And while there are many ways to write a grammar for the same language, only some of them may be accepted by the tools. And as we'll see, there are cases where it's necessary to modify the grammar in order to get the tools to accept it. This happens actually sometimes as well with regular expressions, but it's much less common. So normally, for most regular expressions you would want to write, the tools will be able to digest them just fine. That's not also true. That's not true of an arbitrary context-free grammar.